Okay, so we're halfway. We saw what conclusions we can draw about EY and BZ from this equation. Now we have to use Faraday's law. And just as previously I started by saying, let's consider a certain red rectangle, I'm going to start the same way, but a different red rectangle this time. This time we're going to have a red rectangle that's oriented in the E direction, which means it'll be oriented along the Y direction. And you can see it in the diagram here. I'm going to go a little more quickly this second time. So I want to apply Faraday's law to this new red rectangle, which if I draw it in a way that's devoid of context, looks like this. And I'm going to do the contour integral around it like this. So I want to do the contour integral around it. And what contour integral am I trying to do? Well, I'm trying to evaluate the left-hand side now of Faraday's law, this one. So I have, on the left-hand side, I have the integral of E dot ds. And what will that give me? Well, again, I'm going to make this separation a delta x. I'm going to make this long length an L, and this L is going to drop out of everything. And the electric field is pointing up. So with this time, when I go along this side of the contour, you can see in the diagram, the electric field is pointing up. So when I go along this side of the contour, I pick up a positive contribution, which will be EY at x plus delta x comma t times L. And then when I come back down this way, I pick up a negative contribution minus EY evaluated just at the position x, because this is x and this is x plus delta x. Okay, so that's the left-hand side of the equation. The right-hand side of the equation is minus. Remember that minus, that's Lenz's law. We spent a long time understanding that minus sign in Faraday's law. Minus d by dt of the surface integral of b dot n dA. And there is a b here. And this b is, it's the blue arrows in the diagram. And it's coming from me towards you. And so when I do the surface integral, what do I pick up? Well, I pick up, well, there's this minus sign, and then there's a bz and a d by dt, and then there's the area of the rectangle. So I'll put the d by dt here, and then the area of the rectangle is L delta x. The only thing varying in time is actually the bz. And so now I'm going to collect these, set them equal to each other. The L's will cancel again, L, 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 all the L's are gone. And I'm going to put the delta x underneath on the left-hand side again. And what I'm going to get, when I take this delta x and put it underneath on the left-hand side, I'm going to get EY at x plus delta x and t minus EY at x and t divide by delta x. And that, what's that equal to? It's minus d by dt. And this delta x, well, I put that downstairs already. This L has canceled, and so all I have left is bz. And so I've derived the partial differential equation that partial with respect to x of EY has to be equal to minus partial with respect to time of bz. So if this pattern that we're trying to analyze, in which there's an EY and a bz that depend on x and t, but they don't depend on y and z, and this pattern, I said, is going to end up moving in this direction. If this setup is going to solve Maxwell's equations, then in particular, if it's going to solve Faraday's law, which is right here, it has to be the case that d by dx of EY is minus d by dt of bz. And notice what this says. This says that if EY is varying with as a function of x, which it certainly is, it's got this wavy solution. If EY is varying with x, then bz can't be standing still. So remember, previously we concluded that if BZ was varying with x, then EY can't be standing still. Now we conclude that if EY is varying with x, then BZ can't be standing still. And so the overall conclusion is that we find solutions in which EY and BZ are both varying with x and are both not standing still. They have to be moving as a function of time. And so our task next is to put this equation and the one we derived in the previous video, to put them together and see how waves emerge. But it should, at this point, actually be intuitive to you that what we're going to get is a moving pattern, namely a traveling plane wave.